Okay, good morning. So today we're going to continue talking about multiple regression and then differences and differences, which is kind of like the main estimation technique that you're going to see in a lot of the papers that we go over in the course. But in order to even talk about differences and differences, we have to get to the regression stuff first because it gets implemented as a regression. So on Friday, I started to introduce multiple regression, which is basically just an extension of normal linear regression where you have multiple x variables on the right-hand side of your equation rather than just a single x variable. And the motivation behind this typically is that it's not that we necessarily care about the effects or the relationships between each of these x's and the outcome. It's really more often the case that we care about the relationship between the first x and the outcome. We call it like the coefficient of interest because it's the one we're interested in. And we need to include the other x's because we think that they're essentially factors or omitted variables that could be correlated with the x that we're interested in and might also affect the outcome. So basically these are like confounders, and if we include them in the regression, then we can control for these variables. So let me just talk about this in the context of our air pollution and hospitalizations example. So here y, the outcome, is again going to be hospitalizations. X1 is air pollution, and X2 will be the daily maximum temperature. And I here is going to index days because we're looking at like the number of hospitalizations on a given day and the air pollution on a day and the daily temperature on a day. So the multiple regression model then is going to look like y as a function of the intercept beta naught, the first variable x1, which is the air pollution, and then x2, which is the daily maximum temperature. And so the idea here, or the goal we're trying to achieve, is that by including temperature in the regression, or the reason that we're including temperature in the regression, is that we know that temperature and air pollution are both correlated. So we're not going to be able to estimate a ceteris paribus effect of air pollution on hospitalizations unless we can hold constant temperature, right? Because remember, we want to sort of think about the effect of variations in air pollution when all other factors that could affect the outcome are held constant. And so in particular, we think that maximum temperature, we know maximum temperature is something that varies with air pollution. Like you could collect data and I can show you that that's true, that there is a correlation between those two variables. So we think that, okay, given that it's correlated with air pollution and is something that could affect hospitalizations, we're going to need to find a way to essentially hold it constant or control for it. And the way that we do that is by including it in the multiple regression. So the key then, when you're thinking about variables that you would need to include in a multiple regression, what you want to think about are ones that satisfy two conditions. First of all, they're things that actually affect the outcome. So it's something that has no impact at all on the outcome, then you could put it in the regression, but there's not really any point, right? So the idea is, let's suppose that we have a variable that's completely unrelated with the outcome. If we put it in our regression, then in theory, if we have a large enough data set, what we should estimate is that that when x, so let's just call it like z, just so we don't have to worry about the little subscript they're running around here. So we put z in our regression. What we're going to find is that on average, when z changes, there's no change in y, right? Because y and z are totally unrelated. So we have z there on the right-hand side of our regression. And so if we have a large enough data set, the way that will manifest itself is that the coefficient on z is going to be estimated to be 0 or something very, very close to 0. So what we're doing, like the scenario I'm describing is one where the variable doesn't belong in the regression anyway. If you put it in the regression, that's actually not a huge problem because with enough data, you're just going to estimate a 0 coefficient on that variable, which is the same as not putting it in the regression, right? Like I could put it in multiplied by 0 and then it just disappears. So there's not like a huge downside to including regression or including variables that don't belong in there, but there's really no benefit either. If it's something that doesn't need to be in there, then you're not going to gain anything by putting it in there. So the two conditions that you would be interested in terms of thinking about variables that belong in the regression are, first of all, the variable should have some relationship with the outcome, and then also it might be correlated with x1, which is the variable that you're interested in. So what might be somewhat less obvious, but is nevertheless true, is that if you have a variable that's related to the outcome but is actually like completely uncorrelated with x1, then you don't need to include that variable in the regression. There's still some gains to doing so in terms of statistical precision. Basically, you might be able to like come up with somewhat more precise estimates. But in terms of getting an unbiased estimate, one that's not biased by omitted variables bias, it's not necessary to include that variable in there. And maybe the best way to see that is to think about like the randomized control trial, right? So if we're running a clinical trial, so let's say we had the blood pressure drug that we're trying to test. So yi is individual i's blood pressure, and then xi is what we'll call a dummy variable for being assigned to the treatment group. And we're going to randomly assign people to either treatment or control. So if you're assigned to the treatment group, then you have x equals 1. If you're assigned to the control group, then you have x equals 0. We run the regression of yi is equal to beta naught plus beta 1 xi plus ei, which is everything else that determines blood pressure. So we discussed before that since x is a dummy variable, the interpretation of beta 1 in this regression is just going to be that it represents the difference between the mean of y, the mean of blood pressure for the treated group, minus the mean of blood pressure for the control group, which is the difference in means. And you can think, so that's what it represents. And we discussed because of the random assignment, it's going to also give you an estimate of the causal effect of the blood pressure drug on somebody's blood pressure, because we know that on average, all other factors that might affect blood pressure must be balanced, at least on average, between the treated group and the control group. So there aren't any other factors that are somehow higher or lower for the treated group, and that therefore might confound our interpretation of that coefficient. So that's what I'm sort of describing there is a situation in which, because of the assignment of x, we know that x must be uncorrelated with all of the other potential confounders. That's not to say that there aren't other things that might have explanatory power in thinking about like what determines the outcome. So this is blood pressure. So let's say zi is somebody's age, or even let's say like zi is your sodium intake. So we know that sodium intake is correlated with high blood pressure, and in fact, I think there's like pretty strong evidence there's a causal effect of sodium intake on blood pressure. So one of the things that, like, if you have high blood pressure, one of the first things that your doctor will say to you is like, well, you should try reducing your salt intake, right? So it's certainly the case that if you had data on each person's sodium intake, or say average sodium intake per day over the last 2 years or something like that, and you put that into the regression, that would probably have explanatory power. Like that would have, zi would enter with a non-zero coefficient if you include it in that regression, because it is in fact going to explain some of the variation in people's blood pressures. By variation, I mean like variation across different people, their blood pressure when you take it. So it's not the case that this is a variable that has no relationship with the outcome, but it is the case that it's a variable that's uncorrelated with xi, right? So again, xi is whether or not you're randomly assigned a treatment or control group, because it's random, we know that it can't be correlated with people's sodium intakes, right? So this is a case where you don't, even though Z does have some relationship with Y, you don't need to actually control for Z in the regression, because by construction we know that it's going to be uncorrelated with X, so it's not something that could be on average higher or lower for the treated group relative to the control group, and therefore could introduce some variables. So both of these factors need to be true. The variables that you want to include in there, both are ones that should be related to the outcome and that should be somehow correlated with the X1, the variable that you're interested in estimating a causal effect for. Okay, so the important choice in multiple regression is just going to be determining what variables need to be in the regression itself, so what you want to actually include. So in the example that I gave before, the example up here, you just have two right-hand side variables. The first one is air pollution. The second one is the daily maximum temperature. I'm going to use K here to represent basically the total number of variables that you put in the right-hand side of the regression. So in this case, K is just equal to 2 because you have two variables on the right-hand side. That gives us the following multiple regression model. So now I want you guys to just do a little bit of discussion in your groups and come up with answers or at least ideas for the following questions. So first of all, we have this regression model that I wrote up. In that model, I want you guys to tell me what the effect of a 1 unit change in X1. A 1 unit change in X1 is the effect of a 1 unit change in X1 on Y, with X2 and EI being held constant. Second of all, if you ran a simple regression that was just Y equals alpha plus beta X1 plus U, so basically if you did not include X2 in the regression, would you expect the beta in that regression to equal the beta 1 from above? Third, name another variable that you think could plausibly appear in EI and therefore might be something that you want to include in the regression. And if you do, so if you come up with this variable, do you think that including it in the multiple regression is going to affect the estimate of beta 1? So basically, relative to the baseline up there where you have X1 and X2 in the model, if you come up with another variable and include it, do you think that the beta 1, the coefficient of X1 is going to change when you re-estimate the regression? And then finally, how does your answer change if X1 was randomly assigned? So maybe take about probably like 5 or 6 minutes or so to discuss these questions in your groups, and then I'll ask for volunteers and or call on groups depending on how many volunteers we have. Feel free to ask me like clarifying questions about the questions. Okay, so you guys should wrap up your discussion in the next like 60 seconds, if you're not already. Okay, so is there a group that wants to give us answers for, say, the first couple questions? You guys have volunteered my time before, but you'll get your chance. You guys are group 4? 2? No, sorry, I'm 3. You're 3. You're 2? Okay. Does any other group claim to be 2? I don't think so, right? I think you actually are. Okay. So what's the answer to, what do you guys come up with for the first question of what's the effect? Okay, excellent. And so just, so assume probably all the groups came up with that, but just in terms of what you want to think about for for deriving that if it weren't sort of intuitively clear, is you want to think about taking basically marginal effect, calculating marginal effect of x1 on y, so that would be the partial derivative of y with respect to x1, since y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus e, then that's just going to be equal to beta 1. And the key there is that we said we're holding x2 and e constant, so you can treat them as being constant with respect to x1. Obviously, if they were varying with x1, then you would have a bigger problem, because then you'd have to think about the change in y for 1 unit change of x1, where x1 is also having an effect on one of these two variables, or potentially both of them, and that would be then it would not just be represented by beta 1. So then for the second part, what did you guys say? Okay, and what was the reasoning behind that? Okay, and do you guys have a prediction about whether? So you have a prediction. I know this wasn't part of the question, but do you guys have a prediction about whether beta in the first regression would be larger or smaller than beta 1 in the, or beta in the simple regression would be larger or smaller than beta 1 in the? You think it would be larger? Okay. Yeah, that would be my guess as well. Just because the x2, so when temperatures are high, depends on the air pollution you're talking about. But in general, a lot of pollutants when temperatures are high, pollution tends to be higher, and furthermore, hospitalizations tend to go up also during heat waves. So you essentially have a positive omitted variables bias there, and that some of the positive impact of x2 would essentially load onto the coefficient x1 when you don't have x1 in the regression. So good work. And can you guys just write down the people who are there in your group today? So I think you have like 5 people, right? Okay, so do you guys want to do the next few questions? So, okay, so did you come up with a variable that might appear in EI?
Yeah, we figured like crime rates would higher crime rate than data.
Sure. And do you think that that's correlated with x1?
Crime rate and evolution.
Yeah. Yeah, I need to if you're talking about x2, that potentially actually would be, in the sense that crime rates tend to be higher, I think, when it's hot. Certainly when it's like very cold, I think they tend to be lower because nobody goes outside with maybe criminals and potential victims. But for x1, yeah, I don't think there's any reason to believe that air pollution would necessarily be correlated with crime rates. So then, given that, then for the next question, do you think that including that variable in the multiple regression is going to have a substantial impact on beta 1? And that is because it's not correlated with x1? Sure.
What about like if you did like car accidents or something that had to do with like fatality in cars?
Mm-hmm.
Because the more cars, the more air pollution, the more like also when the cars crash, it's usually like
Right.
smoke or, like,
Sure.
pollution.
Yeah. Yeah. No, that is potentially possible. So I think that, right, if you had it, basically, if there were days on which there were just more cars on the road for whatever reason, because of like special events or because it's a weekday versus a weekend or something like that, that would probably have some relationship to air pollution. And you're also right that it would potentially have an impact on hospitalization. So there's something where it would be correlated with both x1 and y, and then including it could potentially affect the value of beta 1 that you estimate. And then finally, if air pollution were randomly assigned, well, okay, so in the first scenario you gave beta 1 didn't change anyway, but in the second scenario, if air pollution were randomly assigned, then presumably you wouldn't really be worried about other variables. Was there another team that wanted to share? Somebody else was raising their hands.
Well, just can you sort of take what Mr. Hughes wrote and say that higher crime rates would be correlated with the lower area of equation is correlated
With pollution? Yeah, so that would certainly be true on a spatial analysis. But if you'll remember, so it wasn't on this slide, but when we were talking about before, I was saying that I was going to be like indexing time basically, so it'd be daily hospitalizations. So it wouldn't matter in that scenario. But you're absolutely right that if we were instead sort of looking at like hospitalizations by neighborhood or something like that, and air pollution by neighborhood, then there'd be a lot more potential like omitted variables that you could think of. So this, to be frank, like in this particular analysis, it's not, in this particular regression that I put up, it's not so easy to come up with omitted variables. Like in a lot of cases, it's really easy. You're just like, oh, geez, there could be a million things that could be correlated with the variable of interest and the outcome. But here, because it's basically things that have to vary spatially, or not spatially, temporally, at like a high frequency, it's not so obvious. So I think like I kind of overheard your guys' discussion, I think about like age or something like that, which is something, if you had like individuals' age, or in this case, it would have to be sort of like the age profile of the population of people who could be hospitalized. That would certainly be like highly predictive of hospitalization because it's very like hospitalization rate is very steeply increasing in age. But that's not something that's going to vary like day to day in a region, right? Because basically the age profile or the age composition of the population does not change. And so I think you guys are correctly rejected that as a potential confounder. Yeah, definitely right. So I kind of mentioned that also with the traffic thing, but yeah, sort of a weekday indicator is something where you would think that could potentially certainly be correlated with air pollution and potentially also with hospitalizations, just depending on like if people are more or less likely to get into accidents at work or something like that. Okay, so that's great. Let me just record. So you guys are like 7, right? You guys are 1, and then you guys are all present, I think, right? Huh? Yeah, but you're all here, right? You only have 7, I think. Okay, so can you guys just write down the 5 people who are here? Okay. So the problem, as you can kind of gather from our discussions, is that with multiple regressions, you might not necessarily have data on all the variables you need. So basically, like, if you want to convince somebody that you've estimated the causal effect of this X variable on an outcome, what they're going to do is they're going to sort of try to come up with, like, so if you're in a seminar presenting this, basically the people in the audience would try to come up with ideas about variables that could be correlated both with X and with the outcome of interest, and that you don't, or you haven't included in your regression. So if the things that are in your data set and you just didn't bother to put them in the regression, then it's like super simple to just go and add them. But the problem is that often they'll be able to think of variables that you don't have data on or that you couldn't possibly have data on. So